Not. Okay.
Yes, sir.
Okay, thank you. And you can hear my voice also clearly, no? There is no doubt. Okay.
Yes, sir.
Okay, then let me get going. Yeah, good morning, dear friends. So, so the course name is Digital VLSI Circuits, EC 60204, and we are going to discuss about what prompted us to study the subject. So, some parts we discussed yesterday. That means the advancement in integration technologies, fabrication technologies have led. This was the driving force and large-scale system design, but the motivation came from the compulsion to use the integrated circuits for high-performance computing, telecommunications, and means low bitrate video coding, consumer electronics, and also we saw that there is some dissimilarity in the growth of processor-based circuitry and the memory-based circuitry. Memory-based circuitry showed a steady growth of 1.5 per year, that is roughly, okay. Now, the reason is that the memory circuitry are more or less regular in configuration. There is not much change. So that means, as you know, that more or less you have heard of two-dimensional placement of different memory cells, and nowadays the 3D ICs are also popular. So for memory cells, the individual memory cells can be put in a regular fashion. But for the processor, there is some what you call a sort of irregularity. That means with the passage of time, more and more functionalities had to be incorporated. Okay, like initially only binary processing was allowed. Later on, the arithmetic co-processors were brought in, and then onwards, as you remember, that for digital signal processor, some components like MAC, that means multiplier and accumulator, okay, and say shifter and various forms of what you call parallel multiplier and so on, so were incorporated in the particular silicon wafer, and that led to some irregularity in the placement of different logic units, and the interconnection complexity grew. So to house so many interconnections in a same silicon wafer, the logic more of the space in the integrated circuit chip was taken up by the interconnection. So if you'll be, I believe all of you know that nowadays in a typical processor chip, more of the space is occupied by interconnections rather than the actual logic units. Okay, so this you can study at your own leisure time from internet. Okay, now next, let us take up this concept of VLSI design flow. What do you mean by that? We know that the VLSI design process is evolutionary in nature. It's quite, it is gradual. It is not, not at one go, we cannot realize a particular chip. Suppose we have decided to design a, let's say a processor chip. Okay, so then what we start with, we have to have a rough floor plan. Okay, and then onwards we start bringing in, that means at the very beginning, we have got totally abstract concept, and later on we try to bring in the what we call the concrete items by and by. Okay, so for this VLSI design flow, this is a very celebrated uh, Y chart. As you can see that in the form of a Y diagram, we have got different axes or different planes like behavioral domain, structural domain, and the geometrical layout domain. Oh, these three are the three principal domains. Okay. Now, when the process starts at the very beginning, we have got the simple in the form of a algorithm. It is there. Say we want to build up a kitchen timer. Okay, then we know that to start with, we decide that a timer is there. Okay, and then what are the different components? Or for example, if you have got a processor, apart from the CPU or the central processing unit, we need to have a, say, program counter, stack pointer, general purpose registers. Now, to start with, we have got uh, a, a rough floor plan, okay, like a two-dimensional box, or let us say a layout, where we know that here and over also rough coordinates are there. Okay, so that means suppose we want to place the CPU centrally, then on its right side the GPU, the general purpose registers, and so on. Okay, so first we start with the algorithm. So let us see. The Y chart we show here on your left provides a simplified design flow for most logic chips, and this was uh, arrived at by a group of scientists who were doing their research in University of Guelph, Canada. Okay, the principal designer was Daniel Gatsky, and one Indian gentleman was there, Nikhil Dutt. Okay, you can see at the if you type the names Daniel Gatsky and N Dutt, okay, DUTT, Nikhil Dutt and Daniel Gatsky, their teams worked out this Y chart. They were taking up the high level synthesis. Okay, so you will find many papers by them, by this duo, Gatsky and Dutt, in on high level synthesis. This Y chart, what does it provide? It provides a simplified design flow. I mean, the activities that take place. So first to start with, the principal three domains of representations are there: behavioral domain, structural domain, and the actual layout domain, geometrical layout. So it starts from the algorithm that describes the behavior of the target chip. So if you want to build a microprocessor, we understand that based on the user program, okay, which will be in the form of a sequence of instructions, each instruction will be executed. Okay, now how it will be executed? For that, you need either completely hardwired control unit or microprogram control unit. Okay, so whatever be the process, you and again in the microprogram control unit, you can have horizontal microprogramming or vertical microprogramming. Okay, so each of them is an involved mechanism. Okay, but to start with, we have just a rough or abstract view. That means the user will present with a set of instructions, okay, sequence of instructions, and it will be executed by the microprocessor, and the results, the final results will be outputted to memory, something like that. So to start with, this algorithm, and we have got a rough view of what will be the components, the principal components of the processor. Okay, and then we come down to the geometric layout, that is a floor plan. Okay, so it's like a single box. Okay, where the different components will be there, but that cannot be the end of the end goal. So now we need to come to the more concrete items. Then we come back to the next lower level of behavioral domain. In that means we visualize the our design system as a finite state machine. The finite state machine means what? The number of states through which the system will progress will be finite in number. Okay, to start with, see, you switch on the system. Okay, then after doing some housekeeping operations, that means just checking up the memory whether they are free from any corruption. Okay, then we start to wait for the first instruction from the user. Okay, and this is the initial state maybe, and then based on the user given whichever be the instruction, whether it is reading from the memory or whether it is just say clearing the contents of accumulator or sending some or just keeping up the storage on the stack, whatever be the job, the finite state machine waits for the first instruction from the user. But that is again on the behavioral domain. Okay, so in the shape of the hardware, you have to implement this. You have to realize this finite state machine. How do you do that? That is by means of a set of registers and arithmetic logic unit. Again, so you have got a what you call a on the again this is much more abstract. Okay, so what you do, you need to come down to the geometric layout domain. That means on the given uh, floor plan where you are going to put the ALU and the registers. Okay, so that means placement will be concerning you. Now again, this is also quite abstract. So now you going more and more towards the concrete details. Now you get back to the behavioral domain. Then module description. Module description means what is the constituents of register, which is a 64-bit register or 128-bit register, and ALU, how it will be designed, and so on. Okay, so that means arithmetic logic unit. It may be consisting of uh, two what you call operand buses, and then what exactly is the constituent, how many arithmetic functions will be there, how many logical functions will be there. For that, planning should go on. Again, that is on the behavioral domain. Now you come back to, in the structural domain, the leaf cell. That means in order to implement the module, what is required. Now leaf cells means normally this is stored in the library. So some subsystems that already has been designed, implemented and tested thoroughly, and they are placed in the library. Okay, so leaf cell may consist of different units. A full arithmetic logic unit may itself be a leaf cell, or you can have the uh, the logical units. Another leaf cell can consist of arithmetic units and so on. Okay, but again, in the on the geometrical layout, where you will place the actual the components, that will concern you. Next, in order to realize a particular, say, logical unit, that means the set of what are the logical operations you require, maybe XOR, and or, okay, the set of complete set of the logic functions. Okay, again, in place, in case of arithmetic functions, what do you require? Do you require two's complement operation? Do you require multiplication, or do you require subtraction? Okay, all these things will concern you. So this thing you need to work out. And what are the Boolean equations corresponding to that? That means in the lower functional level or behavioral level, you have got all the Boolean equations that will concern you. So for example, we know that for a full adder, there are carry output function, sum function, and so on. But it can be as complex as performing a multiplication operation also. Next, these operations need to be realized only by means of gates. Okay, so or an individual gates are realized in the form of transistors. Okay, but how do you realize the transistors? How do you realize the individual MOS transistors? For that, you require the mask. So at the very basic level, you have got the masks of the transistors. Okay, this is the most basic level, but this is a very simplified view. Okay, okay, so that means it is actually the levels of evolution, you can say. We start with the most abstract and end up with the most concrete. Okay, at the most concrete level, you have got the masks for the transistors. And the masks, you can now thoroughly checking the placement of the transistors so that there is no what you call overlapping or shorting of the transistors. After ensuring this through a set of design rules, you need to uh, send out the layout to the fabrication house, who will come out with the actual what you call silicon real estate, right? So thereby the chip gets fabricated. Okay, so these are the various levels of we have seen. I think you will learn in detail on this Y chart in your VLSI CAT course. Now you have got again a set of what you call stage wise approach for designing a VLSI chip. Again, you start with the algorithm or the system level. Okay, and then you go to functional or RTL level. That means you start from the most abstract and down to the most concrete. Okay, and in the functional level, also it is sometimes called as architectural level or register transfer level. So RTL means register transfer level. Again, as we have just discussed, that you need to have a set of registers and ALU, for example. Then how the registers and ALU can be implemented? They will be implemented in terms of the gates. Okay, again the gates will be implemented in terms of the transistors. Okay, so transistors will need to be realized in the form of the say basically each of the transistors, each of the millions of transistors, everything will need to be realized at the fabrication house. But before that, you come out with the physical layout. A very popular geometric layout is given by GDS2 stream format. Okay, we do not need to know the details. If you are interested, you can just study about that. Okay, so but these are the various steps. Okay. Now again, we are in the realm of history. So if many copies of our desired system, say we are designing a mobile phone set, okay, that has got different components apart from the communication equipment, you may need to have a camera, you may need to have a different components, okay. But the basic most important unit is the modulator and demodulator, okay. So everything needs to be designed and implemented. But if you have to have many copies of the desired system, reliability is required, high reliability of operation and a proper balance among the cost and performance characteristics such as timing, area and power need to be ensured. So which logic elements will choose, select, so that you can have the best possible timing. That means the maximum speed is ensured, least area is also can be realized, and the power, okay, power should be least. Note that here, for simplicity, we are not showing some of the feedback loop. But please remember that inside the Y chart as well as this simplified diagram, there are always some back annotation. That means, suppose having come down in the physical layout, you find that if you have to accommodate those millions of transistors, the targeted area cannot be, the targeted area may be too small. So then we have to go back to the algorithm level or function level and cut out and cut back some of the say features. Okay, that means all the features may not be possible. Suppose you have got a earmarked area for your mobile phone, and you have in the plan, in the algorithm plan, you have got that I'll put different apart from the basic communication equipment, I need to put the camera and all this. But the targeted area is smaller. So you come back to the algorithm level and remove some of the components, like the camera, you cannot house it, something like that. Okay. And so that is dependent on the preliminary cost estimate and all that. Okay. So always there is a place for feedback loops. And MOS process, this is the most prevalent technology. You may be knowing that in different circuitry, like space circuitry and so on, we have, the electronics engineers have used MMIC, that means mic, monolithic microwave integrated circuits, okay, built on gallium arsenide or MESFET, okay, but they provide us with good speed, but on the downside, the area requirement at the very beginning, the processing technology is quite complex. Also, power consumption is too huge. But MOS circuitry, on the other hand, provide us with the benefit of low power and low area that can be realized through MOS. Although the speed-wise MOS is behind bipolar transistors and also gallium arsenide circuitry, but still MOS is still now the most popular, most prevalent technology. And in the integrated circuit industry, different geometries that we talked about are there. And in general, it has been found that every 3 years there is a downscaling of by 0.7. That means now today, if you are able to accommodate a huge amount of circuitry within say 1 micrometer by 1 micrometer, after 2 years or 3 years or so, you can house it within say 0.7 micrometer into 0.7 micrometer. This is the normal trend that has been observed, okay, in the trend of what you call progress of fabrication technology, okay. Through 1990s, these were the channel length, okay, but now with the advancement in photolithography, okay, we now have the very what you call smaller and smaller channel length that is realizable. Say currently 1.14 nanometer or even 7 nanometer has been realized. Okay, and also copper, as it is the better conductor with respect to aluminium. So copper wire has replaced aluminium mostly. Okay, so because then you have got lower IR drop. In the deep submicron era, the submicron means whenever the channel length is lower than 1 micrometer, we talk about submicron. And deep submicron means that the channel length or the feature size, okay, is becoming much smaller and smaller with the progress of time. So we talk about deep submicron era. Okay, so it is controlled by a number of short channel effects. Short channel means the channel length is becoming shorter and shorter with day by day. So what is the on the downside, we have got extra RC delays due to wires connecting transistors. So RC delays cannot be prevented, and coupling between lines are also there. So that means there can be capacity, what you call effect or inductive effect, and you have got induced EMF, induced voltage. Due to these things, the delay can differ. Also, noise injection will be there. That means something undesired has come out, has been implanted, in addition to the desired signal. Okay. Then increase in the resistance leads to voltage or IR drop and drop in power grid. Metal migration is also important. What do you mean by metal migration? At high current, we see that the metal ions tend to flow in the direction of the conventional current. Metal is positive mostly. And then what happens, due to non-uniform width of the current conducting wires at some point of time, due to high current, okay, as metal ions tend to migrate, we normally see that there can it can result in a void or discontinuity at the middle of a wire. So then the signal cannot flow to the desired destination, right? So this is just an example of a undesirable effect of the what you call relentless downscaling of sizes. Okay, so metal migration, but at the same point of time, you have to tackle it by probably reducing the current, keep giving a cap to the maximum current that can flow, and reliability of aluminum lines suffered. That's why copper has mostly replaced aluminum. The above issues are signal integrity. That means whether the signal can be maintained, can be preserved at the proper values. It will have a what do you call undesired fall maybe. Now with the continued scaling, line width has come down. This you can just study, is very much historical. Okay, so we talk about something like low K dielectric. Okay, now what is K? K is the dielectric constant. Okay, now C equal to epsilon A by L. So if you have low K, okay, lower K dielectric, then the capacitance will be reduced and we have got better switching speed. Okay, the RC delay will be reduced. Now again, I just mention some of the problems that will be encountered on the deep submicron device side and also deep submicron wires or interconnect, right? So please note that we are not going into details at the today, but whenever. Okay, Tausif, you can hear me. Hello.
Yes, sir, I can
Okay,
hear you.
okay, thank you. If anything tends to be unclear, please let me know. Okay. Achha, so from time to time, I'll ask you some questions. Please keep yourself agile, because some part of your what do you call this course will have test and all that. I'll announce that also. Don't worry. And also, but at the same point of time, I want to check whether you are attending in the class. So I'll take attendance today. I'm not taking it. Let me take it. And also, from time to time, I'll ask you simple questions. So please be aware. Please be agile. Okay. Please interact in the class so that this will also form the part of your what you call internal assessment, that you are attentive in the class, you are in sync with the class. That will need to be tested. Okay, I am not like that suddenly taking a test and all that, no, but from time to time I'll ask you questions. Okay, so as we can see now, yeah, attendees are good, 53 have attended, but I need to again, let me see, I'll just take the attendance, so download the attendance list. Okay, thank you. So yeah, so let me go about. So on the deep submicron device, what are the features that we need to be aware of? First is short channel effects on VT. Now what can be VT? VT is threshold voltage. Okay. Note that B with capital T we are writing, that is the technology threshold voltage. Again, the threshold voltage will split into different components after some classes. Okay. So on what threshold voltage depends? Okay, that we'll discuss in depth after some time. But short channel effect means that whenever you are going from conventional long channel devices to the short channel present day devices, the threshold voltage need to be recomputed. At some point of time, it may have to be increased from the actual expression of the conventional device. At some point of time, you may need to reduce, but that we'll see later. So short channel FX means whatever expression of VT we get from the conventional electronics, we need to modify it to some extent based on the geometry of the device. That we'll see later. Now, let me talk about velocity saturation. Okay, this velocity saturation means, you see, with the progressive, with the uh, gradually the distance is coming down. That means the length is becoming smaller, width is becoming smaller, and what else? The width and all that. So your what should I say? The all three dimensions are coming down. But at the same point of time, if you keep the voltage at same point of time and dV and voltage by distance, you give me the field. So the field is going up considerably. Now in the high field, some effect is found like the collision amongst the carriers. So before the in conventional NMOS device, okay, say MOS is a unipolar device, all of us know, is a majority carrier device. What do you mean by that? Say for example, for an N-channel device, electrons are the major carriers. They grow, they tend to pass from the source island towards the drain island through the channel. And while they are progressing, they are traveling at a certain speed. That speed may need to be the speed. I mean, what do you call indiscriminately? That speed cannot go up. Okay, so the carriers attain a saturated or maximum velocity beyond which they cannot go. That is due to high electric field. They always encounter collisions among themselves. So, and after the collision, they cannot regain sufficient energy to take on their journey. So the velocity becomes saturated. Normally, as we shall see, 10 to the power 7 centimeter per second or 10 to the power 6 centimeter per second, this will be the saturated velocity. We will talk more about that. Then you have got thin oxide tunneling or breakdown. Okay, so that means as the oxide thickness becomes lower and lower, that means the distance between the gate, the overlying gate and the underlying channel, the distance becomes smaller and smaller. At some point of time, the oxide can break down. Okay, that means for that different mechanisms are there. Subthreshold current. Subthreshold current means normally uh, theoretically, we say that below the threshold voltage, the carriers cannot move. But in case of sub-threshold current, okay, even though the difference between the voltage of gate and the underlying channel is lower than Vt, sometimes the current is found to flow. That is talked about as sub-threshold current. What are the mechanisms? Okay, that we shall study later. Then DIBL, drain induced barrier lowering, also we shall just briefly touch. Okay, you cannot take huge amount of time on these topics, but these are the effects of the deep thermal device. Okay, that means the barrier will become lower. Again, this will contribute to subthreshold current. Hot carrier effects. Okay, then again the high speed carriers are there. Temperature can grow up, and that also may lead to undesirable effects. Again, thin oxide gate leakage. Some of the mechanisms are interrelated, although we talk in terms of different terminology. And then, as far as the interconnects are concerned, that means the deep submicron wires, they are also with the width coming down, but RC delay, the length is also smaller. Okay, but as the interconnect complexity grows, the signal has to travel a long distance from unit to unit, from logic unit to logic unit. Then RC delays will need to be talked about. Okay, so when the RC delay grows, okay, we need to bring in some buffers in the midway between source and destination. IR drop, okay, IR drop is also important. That means when the carriers are flowing in the channel, okay, drop is taking place, IR drop. So we need to take the possible, what we call the reverse voltage or reverse biasing, okay, due to IR drop. Then LDI/dt capacitive coupling, this will be unavoidable, inductive coupling, because of the fact that in a given space there are a lot of wires going in one direction and in another plane in perpendicular manner or parallel manner, more and more wires are going. So between them capacitive coupling can take place, inductive coupling, and so the undesired voltage will be there, okay, and that can interfere with the proper signal value. Okay. Electromigration we have spoken briefly. But what about the antenna effect? Yeah, this is somewhat interesting. Particularly, you may have got some idea of this when you studied about the VLSI technology. Okay, so what is that? Antenna effect, antenna means that, yeah, you have got different metal layers. Okay, now in the present day, you will find that multiple metal layers can be there. Okay, for a particular chip, and different motivations are there. But what is the effect of having multiple layers is that when in the fabrication, during the fabrication process, there are certain mechanisms. I don't know the details. You can study if you are interested, like say sputtering, okay, or chemical metal mechanical polishing (CMP). So during this processes, what happens actually, charge tends to build up on the metal layers. It is like charges building up or charges gathering or on antenna. Then what will happen? Charge Q equal to the product of capacitance and voltage, C into V. Okay. Now voltage, suppose the capacitance remains same. That means for a given set of the uh, dimensions like area, length remaining same, okay, epsilon remaining same. So capacitance remains same. But Q equal to CV, if Q more and more charge accumulates on the metal layers, and suppose the metal or even the polysilicon which acts like a gate, okay, if more and more charge gathers on the layers, what happen? Capacitance remaining the same, the voltage will grow. That means the voltage drop between the gate and the underlying channel will grow, and due to that due to high voltage and the x remains same, that means thickness remains same, so dbdx will be growing up due to high field. Okay, you may see that it can lead to some channel what you call oxide breakdown. Okay, so antenna effect may lead to oxide breakdown, and that will be undesirable. That means you want the device to remain off but current flows. So antenna effects is also undesirable, but how to take care of that, if time permits, we shall study. Not now. Just we point out to different features for DSM device and DSM wires. These are some of the, you can say, yeah, some drawbacks or problems that are unavoidable. Okay, while we go to deep submicron devices. Again, just to way of some recapitulation, you can say that means here different salient voltages we just bring into your attention. You know all about that, I'm sure, but just to touch upon the basics. So this is, let us say, the logic 1 domain. This is the logic 0 domain. We just show by two rectangles. Okay, that means there is a range of voltages. Okay, that means when you say logic 1 voltage, a particular component at the output of this we are seeing logic 1 and logic. It does not mean that always we shall have perfect 5 volt or perfect 0 volt. No, we can have 3.6 volt and still it will be counted as logic 1. We can have say 0.7, but it will be counted as logic 0, something like that. So we have got a logic, a domain of voltages, okay, a range of voltages. Now on the input side, and this is on the output side. Okay, now why the logic 1 range on the output and input side are different, and that too on the logic 0 side? The reason is that different circuitry are involved, the components are involved, but we are not going into details. This you must have studied in your lower classes. For example, in TTL, okay, on the output side you have got say totem pole circuitry. On the input side you have got multi-emitter transistors. Then what else you need to know? If you remember, there are some phase splitter. So the presence of all those transistors and their interaction will lead to different logic 1 and logic 0 range in the input and output side. But more importantly, we talk about noise margin. That means the allowable difference in the output and input voltage. Okay, if that is violated, we say that the circuit is becoming unreliable. But what is noise margin? Noise margin on the higher side is VOH and VIH, they are different. What do you mean by VOH? VOH is the lower limit of the logic 1 voltage on the output of a circuit, on output of a gate, let us say. And VIH is a lower limit on the, that is lower limit on the input of a gate. So due to noise, due to negative noise or low going noise, if suppose a on the output side the signal is having this value and it is traveling through interconnection and it is coming to the input of the next device. If due to the effect of low going noise, the level of the voltage falls, it will be tolerated if it falls up to VIH, but not beyond. Okay. So VOH minus VIH will be talked about, will be referred to as the noise margin on the higher side. We write it as Nm with a subscript H. Similarly, Nm with a subscript L. What do we mean by that? That means on the output of a gate, the voltage level is say some value VOL. Now, again, as it travels through interconnection wire, and some positive going noise occurs on top of that, then it can bring up the voltage level, and if it does maximum up to VIL, it will be tolerated. So with the VIL, as it appears at the input of the next gate, it will be taken still as a logic low signal. But if it goes beyond VIL, then some wrong interpretation can take place. That means the signal will not be read properly, will not be interpreted properly. Okay. So then NML, the noise margin on the lower side, is the difference of VIL, VIL. So you need to know this definition. We'll make use of that while discussing about the realization of different MOS, okay, MOS inverters and so on. Then this is a very important graph. Suppose the output as a function of input. We talked about that. We refer to this as voltage transfer characteristic. Why transfer? Transfer means normally we see voltages are functions of time. Okay, the signal is a function of time. But you see that here in the two-dimensional curve, input we plot along the x-axis, output we plot along the y-axis. So this output input characteristics is talked about the voltage transfer characteristic. And you see normally this is the inverting voltage transfer characteristic and this is the non-inverting voltage transfer characteristic. This is the inverting circuit. Most of the circuits that we encounter in our course is inverting in nature. Okay. So inverter, you can say, is the crux of is the nucleus of digital logic design. Okay. We shall start our discussion with the inverter, then we shall pass on to the different gates. Okay. Now here, as this goes on like this, okay. So the voltage at 2 points, we have got the slope is -1, and those are very salient voltages. At the lower voltages, we call it to VIL. So input voltage lower at this point, dV out dV in is -1, and the higher voltage VIH also dV out dV in equal to -1. And similarly here, dV out dH equal to +1, dV out dV equal to +1. Okay. So we will talk in details about the voltages. Now you see normally this is another typical time varying characteristic we are showing. This is the input voltage and in response, that means if you have got an inverter, if this is the input voltage, the output voltage is shown like this. Okay. Now input voltage, you see, we have tried roughly to see that if this is the total voltage swing, lower one is VOL, higher one is a VOH. Okay. So VOH minus VOL, if you travel 10% of that, 0.1, you reach this point, then 50%, that means this point is what? What is the absolute value will be VOL plus 0.5 of VOH minus VOL. Similarly, 90% we write, what is the absolute voltage? Absolute voltage is VOL plus 0.9 into VOH minus VOL, right? Voltage swing is VOH minus VOL. Similarly, when the signal goes down, it is like that. And similarly, we have got the output voltage. Okay, if for an inverter, if this is the input voltage pattern, this will be the likely output voltage pattern. Not always, mind you, not always, but typically if the signal transition is smooth, the operation of the circuitry is more or less acceptable, then we see this kind of trend. Now, we have got some concept of what you call propagation delay. Note that always signal will take some finite amount of time to pass from one point to another. Never signal goes, okay, at just what do you call instantaneously signal just cannot present itself at the desired destination. Some amount of time should pass. And to have a rough idea of the time required for the signal or let us say transit time, we have got this idea. First is TR. TR means the T rising. And similarly, so T rising means what? The signal travels the time taken by the signal to go from 0.1 10% point to 90% point roughly. Similarly, falling time is the time taken by the signal to go from 90% to 10%. So for example, let me see that suppose VOL equal to 0 volt, VOH equal to 5 volt. Okay, then what will be the 0.10% point? It will be 1 volt, and 9% point will be suppose VOL is 0 volt. Suppose it is coincident with the time axis. VOL equal to 0 volt, VOH equal to 5 volt. Then 10% point will be how much? 0.5, right? And the 90% point will be 4.5, right? So the time taken by the signal to rise from say 0.5 volt to 4.5 volt will be TR. And similarly, the time taken by the signal to come down from 4.5 volt to 0.5 volt, this we talk about as the TF or the falling time. This is the rising time, this is the falling time. Okay. And next we talk about TPHL and TPLH. These are related. So what do you mean by TPH? This is this we refer to as the propagation delay from high to low. Okay, so TPHL means the time taken by the signal. I mean, this is the time. The 50% time is the input side, and this 50% on the output voltage. So the time taken by the circuit to reach the 50% time while in the output, starting from the 50% 50% point in the input side. So this difference, this 50% and this 50% difference is TPH. Propagation delay from high to low. That means how much time the circuit is taking in response to a positive going wave. Okay, like this. So inverter means that if you have got a rising wave at the input, you have got a falling output voltage at the output. So how much time the output is taking to come down to the 50% point, starting from the 50% point on the rising time. This time is referred to as TPHL, propagation delay from high to low. Similarly, you have got TPLH, that means in response to a low going wave, voltage wave, the inverter shows a opposite trend, that means rising wave, right? So how much time the inverter takes or how much time the output takes to achieve the 50% point in the output after encountering the 50% point at the input side. So this difference is referred to as TPLH, that means the propagation delay from low to high. Okay, any doubt? Similarly, sometimes we also make use of what you call THL, that means on the output side itself, the time taken to go from 90% to 10%, TH, high to low, and low to high, 10% to 90%. Yes, any doubt?
Yes, sir. I have one doubt.
Oh yes, Nilesh, yeah, Nilesh, Nitish, sorry, Nitish.
Sir, the graph that you have shown between V input and time, yes,
Yeah.
the V input. So in the scale, Y scale, it should be VIL, VIH, or VOL, VOH.
Oh,
That
this
is
way, Nitish, you are pointing to
no,
this.
no, sir, second one, adjacent to it.
Oh
Yes,
yes,
sir,
yes, yes.
yes.
Yeah, yeah, yeah.
So here we have VOH, VOL, or VIH, VIL.
Right, right. Good question. Good question. Yeah, yeah. So normally, what we see is that the signal levels, the signal levels or its the extremities of the signal level, we tend to put by VOH and VOL. These are taken to be the, you can say, the absolute. When we design the inverter, it will be more clear. That means VOH is the output voltage when the you talk about an inverter, when the input is 0, then nominally the output voltage is taken to be VOH. Okay, and similarly VOL is the is the output voltage when we have at the input complete VOH or VDD, right? So that point of time, with based on that concept, normally, although we are talking about the input voltage, but the extremity, the higher extremity as well as the lower extremity is given in terms of VOH and VOL rather than VIH and VIL. Normally, VIH and VIL become important with respect to the noise margin. Okay, that means VIH and VIL, we say that as you gradually increase the input voltage starting from the zero voltage, the starting from the zero voltage, as you increment as you gradually increase the input voltage at one point of time, okay, we can go maximum to the limit of the logic 1 level, and again as we continue to increase at one point of time we enter the logic 0 level. VIL and VIH assume importance from the point of view of noise margin. But when you are talking about the voltage measurement, whether be it is the input side or the output side, then VOH and VOL, they become more important. Okay, as far as the limits are concerned, whether the lower side or the higher side, rather than VIH and VIL. Okay, VIH and VIL become more important when you talk about the noise margin rather than the levels, voltage level. When you talk about the voltage level, it is mostly VOH and VOL. Clear? Okay. Acha. Next. Yeah, thank you, Nitish, for your question. Acha. Acha. Next. Again, today, I mean, as we are in a mood to just recapitulate these things, but just recall that how you build up a basic NMOS transistor. So we have got a underlying P substrate. This is important from the point of mechanical support as well as providing the what you call the ground for interesting MOS electronics. Okay, metal oxide semiconductor, M metal oxide semiconductor. Although when metal
Sir,
oxide, yes, yes. Sorry,
sorry sir for the interruption.
yeah, no problem. Yeah. Oh
Sir,
yes,
can
Ankit.
you, yes, sir, can you please explain the point again, like why at the input side that VOH and VOL is of more concern?
Okay. Yeah, here you are showing the trend of input voltage, but normally you see the input voltage, how it is generated. Whatever the signals you are using for various analysis purpose, right? Signals you are using for or you are generating the signals, be it voltage signal or input signal, they are also generated by same signal generator. Okay, and these are obtained at the output of some device, right? Okay, so basically, how do the input signals come into being? They are generated from some source. Okay, by some say in your laboratory when you are working with some potential source, voltage source or current source, they are generated by nothing but some say voltage regulator. Okay, and voltage regulator means that is obtained at the output of a device. Okay, so
Yes, sir.
when you're talking about the output of a device, okay, at the output side, always the voltage levels will be thought about in terms of VOH and VOL, right? So VOH and VOL, they assume importance whenever you are talking about the levels of voltages, be it at the input side or output side. Say the VOH, that means we are talking about plus 5 volt, 0 volt. Normally we have say a general voltage, general diode regulated voltage, or let us say any say whatever a Texas Instrument voltage regulator. So they are generated at the output of a circuit, right? Never at the input. After being
Yes, sir.
generated, only they are fed as input to the subsequent gates, right? So that's why
Okay.
VOH and VOL, always the levels will be talked about as VOH, VOL. Okay, never
Okay,
as VOH.
okay, sir.
Good.
Okay, sir.
We'll talk later also. Acha. So let us see quickly. Just, I mean, you know everything, but just I just want to draw your attention briefly. So here you see, source and drain are two isolated islands on the P substrate. There is a lightly doped P substrate. You have got the source. You have the now. Remember, dear friends, why it is called source? Why it is called drain? Source is the terminal of a MOS device through which the majority carriers enter the device. Drain is the terminal through which the majority carriers leave the device. So in case of a NMOS transistor, N-channel transistor, these are made up N plus means that the The doping density is much higher compared to this. So if this is a 10 to the power 16 or 10 to the power, say 10 to the power 17, 10 to the power 16 ions per cubic centimeter, here you have got say 10 to the power 20, even 10 to the power 21. So that's why it's called N plus. Okay. And L is the channel length. Gate, between gate and the substrate, you have got the oxide or insulator, silicon dioxide, normally silicon. And gate is biased with respect to source and substrate are shorted. So this gate voltage with respect to substrate or source, whatever, VGS, this is a potential source, and between drain and source, this is a potential source. Now this must be there in order to ensure flow of carriers from source to drain. We are talking about the N-channel transistor, where electrons are the majority carriers. Okay. How much time the electrons or the majority carriers take to go from source to drain? That is talked about as transit time, tau. So tau is what? The velocity of the carriers is L by tau, where L is the channel length, tau is the transit time. And also, you know that velocity can be related to electric field. Okay, so this electric field is mu into E. Mu is the mobility. And electricity, we are talking about the mostly the longitudinal electric field, mind you. Longitudinal electric field means VDS, that means drain to source divided by L. Also, we have another transverse electric field, that means the VGS divided by the TOX. TOX means the oxide thickness. But the longitudinal field is responsible for allowing the flow of carriers from the source to drain. Okay, so it is mu into VDS by L. Then the transit time can be related between all these parameters, that is L square by mu VDS. Why it is so? Because tau equal to L by V. And what is V? V equal to mu VDS by L. So in the denominator it will be what? It will be mu into VDS by L. So L twice it is coming in the numerator, so it becomes L square by mu VDS. And the typical conventional value of the electron mobility is 650 centimeters square by volt second. Dear friends, you must remember the units of all physical signals, physical parameters. So never forget that the unit of mobility is centimeter square per volt second. Okay, so twice that length is coming, and in the denominator volt and second. So it is a must that whenever you are doing any problem solving, every physical signal must have a associated unit. Never forget. Okay. And now we relate the charge. Charge equal to what? The product of capacitance and average gate to channel voltage. And how is capacitance related? So here we look upon the transistor as a parallel plate capacitor. The top plate is gate, the bottom plate is substrate. Okay. So we have got the area, the cross section area is W into L, the width of the transistor, length of the transistor. Width I have not shown here. Okay, it is not a three-dimensional picture. This is like a cross section. So imagine that the gate is like a small rectangular parallel pipette. Okay, okay. So that means we have got width perpendicular in respect to the length. So length into W cross section, and capacity is equal to epsilon OX into WL. That means area by TOX. And average effective gate to channel voltage is VGS minus VT. Okay, threshold voltage minus VD. Why VDS by 2? This is assuming that the channel is resistive. If the channel is resistive, okay, you see that at this point there is no reverse biasing. The complete channel voltage is VGS, okay, and as you progress towards it, at this point it becomes VDS is subtracted, needs to be subtracted because the drain is more positive with respect to the source. But in the middle average value here, the channel drop is VDS by 2. Okay, so that's why VGS minus VDS by 2. And since we are talking about the overdrive voltage, so VGS on top of threshold voltage. That means VGS minus VT minus VDS by 2. This is taken to be the average effective gate to channel voltage. And you see the charge equal to what? The product of capacitance and average gate to channel voltage. So epsilon OX into WL by TOX multiplied by this, and then it becomes, what is the current? Current means the conventional current flowing from drain to source. Okay, electrons as majority carriers are flowing from source to drain. Conventional current are flowing from drain to source. The magnitude of that current is given by Q by tau. So you just relate these two. Q divided by tau. Tau is L square by mu VDS. So this becomes this. That is mu epsilon x by Tx into W by L. W by L is very important. This is talked about as the aspect ratio. All of you know that. Aspect ratio, width to length ratio. Okay. And mu epsilon Ux by Tx, this is talked about as the process transconductance. Okay. And you have got the quadratic voltage dependence because VDS square. And this is the expression for non-saturated, linear or triode. So 4 names are given. Okay, I have not shown yet the graph. We'll show next day. Mu epsilon Ex by Tx into W by L. Okay, VGS minus VTS into VDS minus VDS square by 2. This relation, this equation holds good when the device is in triode region or resistive region or non-saturated or linear region. And when the channel pinches off means what? The channel normally, uh, as you progress from the source towards the drain, the channel width decreases. Why it decreases? Because the reverse biasing increases as one proceeds from source to drain. And when with the increase of drain to source voltage, you let the gate to source voltage remain the same. But as you are gradually increasing the drain to source voltage, at one point of time, the channel will become only a point, like a point. We call that the channel is pinched off. That means at the drain side, the channel is merely a point. Okay, but still we see the current is there. So channel pinches off when VGS minus VT, this is the overdrive voltage, this becomes equal to the drain to source voltage. And then we can, this general equation becomes particularized as K prime W by L half VGS minus VT square. So this is the equation holding good for saturation. Now we see, now we show that this is the typical 3-dimensional picture, polysilicon gate. Now you can see this is the channel length, this is the width. Okay, this is the TOX, gate oxide thickness, typical feature. This is the symbol for a transistor. It is almost like a 4-channel device: drain, source, gate, and body or substrate. And normally we also in the deep submicron devices we see the existence of STI or shallow trench isolation. What is this shallow trench isolation? That means to isolate the devices, the transistors from between one. Say in a silicon wafer, you have got billions of transistors and all of them should be separated from one another. To ensure that you have got the isolation effectively by STI or shallow trench isolation. Shallow means not deep. There is a P well. If you have the by the twin tap process, all of you are aware of the terminology, I believe. Say twin well process or twin tap, the NMOS transistors are fabricated on P well, PMOS transistors are fabricated on N well. And in order to isolate any pair of devices, we have got STI or shallow trench insulation between them. What is that? In CMOS circuit, all devices are enhancement mode devices. They are separated by oxide regions using STI method. Double well or twin tap process, both N channel and P channel devices are created in their own wells. After forming the gate and source and drain, see after these sources and drain are formed, okay, then what you do? You just you introduce oxide, okay, deposit oxide in between. Okay, by what do you call just digging out. That means you remove the remove some of the material through etching process and then pour oxide. So after forming gate and source drain, devices are isolated by etching the trench in the substrate between the devices. So trench is filled with oxide. And shallow trench means not very deep. Okay, just up to this, so that this will effectively isolate to device. Okay. Any doubt up to this point? Hello. I'm sorry that I have not taken your feedback. Okay. So Alex, Amit, any doubt? Mukul, Nitish, Ankit? Are you there in the class?
No, sir, no doubt. This is
Okay.
Ankit.
No, sir, no doubt.
Okay. Thank you. Dear friends. So, can we continue or should we stop at this? Yeah.
Actually, we have a class now.
Oh,
And,
yeah. So whenever you have got class, or whenever I'm taking too much time, please alert me. Yeah. Instantly I'll stop. Okay. Thank you for your presence. Please join for class on Monday. Okay. Monday 10 o'clock.